So let us begin with lecture 2 of current electricity. So we will be discussing the concept of cells, EMF and internal resistance. So we are discussing concept of cells, EMF and internal resistance. So in order to begin with this aspect, let us discuss about a basic battery. So when we say a basic battery, so we mean to say a battery is a device which is having two terminals, or they are basically two metal rods A and B. So we are calling it as A and B, which is dipped in a liquid solution which is conducting in nature and is regarded as electrolyte. So it is dipped in a liquid solution which is regarded as an electrolyte. So A is becoming a positively charged terminal and B is a negatively charged terminal. So this takes place because of the chemical reaction that is being generated or triggered inside this battery, which is also called as electrolysis phenomena in chemistry. And over here in the external circuit, we are marking a resistance R which is connected between the terminal A and B. So this is what the interior of a battery looks like. In the circuit symbol, we draw this setup in this way. So we draw a battery in this sense, where the bigger line is the positive terminal and the smaller one is the negative terminal, and it is having a certain internal resistance of its own, and the two terminals are connected to an external resistance capital R in this way. So we call this as capital R. This is EMF of the battery E, and this is internal resistance R, and the potential difference which it is exhibiting outside its terminals is regarded as terminal voltage. So in order to start understanding this phenomena, we need to first of all understand that because of the thing which is going on inside the battery, A is becoming a positively charged and B is becoming a negatively charged. That is, a potential difference is generated between A and B. So a potential difference is created between A and B, such that now from the previous examples, or from the previous things which we have learnt, over here I am marking this one as a point A and this one as a point B. So we have referred in the previous cases that A is an example of a positive terminal, which is basically signifying point of high potential, point of high potential, and B is a negative terminal, which is a point of low potential. And because of the potential difference between A and B, current is flowing in the external circuit I, and this is what is regarded as the discharging stage of the battery. So current I is flowing from the positive terminal to the to the positive terminal to the negative terminal, or from the high potential to the low potential. Now the interesting fact is, in order to consider the circuit to be a complete circuit, it is necessary that the current must flow from B to A. So if we say that the current is also flowing from B to A, so we are somewhere saying that the current is flowing from the low potential to the high potential. So over here comes the idea of EMF, which stands for electromotive force. Electromotive force. And it must be very firmly kept in mind, it is not a force. So this is the humor part. It is named as electromotive force, it is not a force. The name is misleading in the sense that it is not a force, it is work done per unit charge. It is work done per unit charge. And when we say what is EMF or how do we define EMF, we say it is defined as the amount of work done in taking a charge Q from the point A in the circuit and bringing it back to that point, such that, or we can say that the potential difference across the terminals of the battery when no current is drawn from it, when no current is drawn from it or it is not connected externally, is regarded as EMF. So we can define it in two ways. It is defined as the amount of work done, that is work done per unit charge, which is basically the work done by the battery in taking a point charge from a point on a conductor and bringing it back to that point, or we can say that it is defined as the potential difference across the terminals of the battery when no current is drawn from it, when no current is drawn from it. So in order to understand this in a complete way, let us again draw an analogy. So in the previous lecture we have drawn an analogy to understand the concept of resistance. Over here we are taking one analogy to understand the concept of EMF. So let us consider it in this way. So let us consider that there is an artificial waterfall that is generated maybe in a wedding ceremony. So we say that the water is falling from this higher level A to the lower level B, and as the water is falling down, it is becoming a beautiful waterfall, an artificial one. So now what is basically done over here is, so over here I am saying that the water is falling from the higher level to the lower level, which is the case with the same A and B, that the current is flowing from higher level to the lower level. Now the same water is repeated from B to A by using a pump over here. So the water that reaches over here is collected and sent to A by using an external pump, so that the waterfall can continue. So that the waterfall can continue. So the work of this pump is equivalent to work of this battery, which is creating the potential difference between the 2 points A and B, where A is the higher point and B is the lower point, so that the continuous flow of water can take place from A to B, or the battery over here is maintaining a constant potential difference between the terminals A and B, so that the current can flow from A to B continuously. So this is the analogy which is useful in understanding what is basically EMF of the cell. Now, when the current is drawn from the cell, the potential difference across the terminals of the cell is regarded as terminal voltage. So we call it as terminal voltage or TV. The potential difference across the terminals of the cell is regarded as terminal voltage, and we say that terminal voltage TV is equal to I capital R. So if someone asks me what is VA minus VB, so I will write potential difference is equal to IR. So we have written it in IR. There is also one more possibility to write it between A and V. That is, we write terminal voltage as EMF minus I small r, where small r is the internal resistance of the battery, where small r is regarded as the internal resistance of the battery. So let us understand the concept of internal resistance. So this is the resistance which is offered by the interior of the battery, that is because of the flow of cations and anions inside the battery, that is the electrolyte solution. So if we consider something like this, that this is the metal plate which is inserted inside the battery, which is becoming A, and this one is the another metal plate which is inserted inside this electrolyte or the battery, which is B, and this setup is placed in this container which is containing the electrolyte. So because of the flow of ions, a current is generated inside it. So inside the electrolyte, current is produced because of the flow of ions between the metal plates. So over here, if I say that the separation between these plates is D, and A is the cross sectional area of the plate, and if we consider that this medium is offering a resistivity rho, so I can say that this is also behaving like a wire. Although this equation is not applicable, it is just to make you understand. Just to make you understand. Kindly note it. Just to make you understand. So all this parameter is going to exert or generate an internal resistance inside this medium. So internal resistance depends upon the cross sectional area of the metal plates or the electrodes, that separation between the electrodes, the nature of the electrolyte medium, and the nature of the electrolyte medium. So this generates an internal resistance inside the battery, and we have something like this. Now, post understanding this, let us come to the concept of terminal voltage. So terminal voltage is basically the potential difference across the terminals of a cell. So when we are considering a circuit like this with an external resistance R, EMF E, and internal resistance small r, so this is the interior of the battery. So the potential difference across this terminal A and B is regarded as terminal voltage, and we write it as VA minus VB is equal to E minus IR, which is equal to I capital R. And we say that in case of discharging of a battery, in case of discharging of a battery, we say that the terminal voltage is less than EMF. The second notable fact which we state over here is, if no current is drawn from the battery, if no current is drawn from the battery, then EMF is equal to terminal voltage, which we have already stated in the formula of EMF. So the potential difference across the terminals of the cell when no current is drawn from it. So in this expression, if I say that no current is drawn from it, that is if I put IR equal to 0 over here, so I can say that the terminal voltage is equal to EMF. So the potential difference across the terminals of the battery when no current is drawn from it is regarded as EMF. So terminal voltage and EMF becomes equal when no current is drawn from the battery. And in the third case, when the battery is charged, when the battery is charged, that is the current is entering the positive terminal. So over here in this case, the battery is in the discharge situation. So if the current is entering the positive terminal, we say that the terminal voltage is greater than EMF. So terminal voltage is greater than EMF of the cell. So all the three possibilities are true. When we talk about the terminal voltage, it can be greater than the EMF, it can be equal to EMF, or it can be lesser than the value of EMF. So all the three possibilities are true whenever we are talking about the terminal voltage of a battery. So now we will begin to understand the combination of resistance. That is, we are trying to understand the external circuit arrangement, combination of resistances. So the first thing we are discussing about is a series circuit. So in this kind of an arrangement, the resistances are connected one after the another in an arrangement like this. And it is connected with a battery of EMF E, and we are considering that the battery is ideal, it is not offering any internal resistance. So the individual resistances over here are R1, R2 and R3 respectively, and we want to reduce this circuit into a single equivalent resistance which is connected across this battery having EMF E, which we call as RS. So if I name the points over here, so I call it as point A, B, C and D respectively, and all the points in between is replaced, and in the equivalent combination we are left with A and D. So when we say that we are talking about a series combination, we mean to say that the current flowing through each resistor is same. The potential difference across them may be different. So over here also we are saying that I current is flowing through this resistor. So if we apply Ohm's law for each individual resistance, I can say VA minus VB is equal to I R1. For the next one, I can write VB minus VC is equal to I R2. VC minus VD is equal to I R3. And for this equivalent combination, I can say VA minus VD is equal to I RS. So if I add all these equations, so we are left with VA minus VD is equal to I R1 plus R2 plus R3, and over here if I equate it with this, so I can say that R series is equal to R1 plus R2 plus R3. It must be noted well over here that the potential difference across the resistances may be different. If the resistances are same, that is R1 equal to R2 equal to R3, so the potential difference across each resistance will become same. Now we discuss about the parallel combination. or the parallel circuit. So for the parallel combination, we are considering that the resistances are arranged across the two terminals having the same potential difference, but the current flowing through them may be different. The current flowing through them will become same if they all offer the same resistance. So it is again connected across an ideal battery offering an EMF E, and I am considering that a total current I is coming out from the battery and is dividing itself into three resistors I1, I2 and I3 respectively. The value of individual resistances is R1, R2 and R3. So we want to reduce this into an equivalent circuit. Which will be offering a resistance R parallel RP, and the total current is I, which is flowing through this resistance RP. So if I consider that the resistance network is between the terminals P and Q, so I can replace this entire network, and the potential difference across the RP is also going to be P and Q. So if we write the equation V equal to IR for the individual resistances, so I can write it as Vp minus Vq. For the first resistor I will write it as I1 R1, and hence from here I can write I1 is equal to Vp minus Vq by R1. For I2 we can write it as Vp minus Vq by R2, and for I3 we can write it as Vp minus Vq by R3. So if we combine all the currents, so we will get total current I, which is equal to Vp minus Vq taken common 1 by R1 plus 1 by R2 plus 1 by R3. So from the equivalent circuit diagram, I can say that Vp minus Vq is equal to IRP, and hence the value of current I is equal to Vp minus Vq by Rp. So from both the equations over here, we can say that 1 by R parallel is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So it must be very well noted over here that if R1, R2 and R3 are same, then the equal current will flow through each of them, each of these network. And otherwise we say that the potential difference across the parallel resistors is same, but current flowing through them is different.